I'd like to introduce Alon Zakai from Mozilla. He's going to be talking about Emscripten, which is compiling LLVM bitcode to JavaScript.
Thank you. Guess you can all hear me okay. So yeah, it's really great to be here and talk about compiling LLVM bitcode to JavaScript, of all strange things. So JavaScript, that's that weird script language that runs in web browsers, right? Why am I talking about that at this conference here? This is an LLVM developers conference, so this might seem puzzling. But the motivation is the following. So practically everything today compiles into LLVM bitcode. Either it's already written in C or C++, or it compiles to one of those, or someone just wrote a new language that has a front end for LLVM. So it can compile practically everything to LLVM bitcode. And on the flip side of things, the web is a platform that runs everywhere. Every new OS has to have a web browser. Everyone has a web browser installed on their machine. And JavaScript is a standards-based language that runs in web browsers. So the web has huge, huge reach. So basically, by compiling LLVM bitcode to JavaScript, we can get close. Of course, we can never get perfectly there. We can get close to the ideal of taking any code and running it almost anywhere. So that's really the motivation for doing something that might really seem odd, like compiling LLVM to JavaScript. So this actually works now. Before I start talking about technical details, I want to show you a few quick demos just to show that this is actually a real thing. So these slides are actually running in a browser. So this is just Firefox. It's not a special build or anything. And this first demo is the Unreal Engine 3. So this is a complete game engine. It's over 1 million lines of C++. Here it's compiled to JavaScript and running in Firefox. And it runs great in Chrome too. It's using just JavaScript and WebGL. So this is all standards-based. Doesn't require any plugins. Doesn't require Flash. And in full screen, you can really just forget that it's, oh, thanks for the sound. You can forget that it's even running in a browser. It just looks and feels like a native app. There's even a little benchmark mode where you can see that the frame rate is very good. So even a very large real-world application like this can run inside a web browser with good performance. Second demo I'd like to show you is the Lua VM. So you can even compile an entire virtual machine, which lets you run just any language you want practically inside a web browser. So this just executed some Lua code. You can tell it's Lua because of the double dot syntax here, which is kind of nice. So even an entire virtual machine. And also you can compile individual libraries, not just entire programs. So this is the Bullet physics engine. And it's used in a JavaScript application. The JavaScript app doesn't even know that it's using compiled code. But this happens to be a compiled physics engine from C++, simulating about 500 cubes here. OK, so of course, usually native builds are the way to go. So I'm talking about compiling to JavaScript, but that's obviously just another option. It's not meant to be better than native builds, which are generally the right thing. But there are cases where JavaScript can be very useful. So imagine, for example, that you wrote a new feature in Clang, and you just want to let people give it a quick test. You want to get feedback. So of course, you can send them a patch, and they could build on their own machine, and that could be fine if they happen to have the setup. Or you could build for various platforms and send them the binaries. Or you could build once to JavaScript and just give people a URL. And that's just the easiest way to get them directly to run the code in their browser. They'll see it. They'll give you feedback. And for use cases like this, I think it really makes a lot of sense. And that's actually not a theoretical thing, so I'd like to show you a last demo. This is going to run, hopefully, Clang in the browser here. So you can write some C code over here, and you just hit execute. And if everything goes OK, this is the LLVM IR generated by that code. So you can see hello world over here. I'm sorry, it's not indented properly, and standard error has these color things messing it up. So this is not polished, but it just sort of to prove that even something like a complete C++ compiler can run in a browser. OK, so with demos out of the way, let's talk about how this actually works. So let's take a quick glance at two unrelated code samples, just sort of set the scene and see what we're talking about compiling into what. So LLVM probably most people here can read this very easily, but it's sort of a low-level, concrete IR with pretty obvious things like load, shift left, etc. Whereas JavaScript is this high-level scripting language that has variables without types. It's dynamically typed. It has the new operator to create an instance of an object. It has strings in the language itself, first-class functions, array literals, object literals, very, very different than the other one. In fact, comparing any two languages, these are some of the more different, I would think. Let's focus briefly on several of these differences, because that actually will get us to the problems we need to solve in order to compile one to the other. So the numeric types in LLVM are kind of the natural ones, the ones that you'd think you'd see, I8, I16, et cetera, float double. These are what map to CPUs. These really make sense. JavaScript has one numeric type, double. So you need to do all your numeric operations using just that. So this already is somewhat of a difficulty. The performance model between these two languages is very, very different. So in LLVM, the types and operations map pretty much one-to-one to the CPU. If you have a 32-bit add in LLVM IR, it's going to be a 32-bit add on the CPU. And of course, the performance might change from CPU to CPU, et cetera, but it's typically fairly predictable. Whereas in JavaScript, you have a virtual machine. You have just-in-time compilers. You have even multiple JITs with type profiling that decides when to switch. There's garbage collection. It's very, very complicated. So it's definitely not predictable. And it's just a completely different model where, for example, if your application is slow, you need to start thinking about all these layers to figure out why it's slow. Control flow is another thing that's different. So both LLVM and JavaScript have functions, but LLVM has basic blocks and branches, whereas JavaScript has ifs and loops, higher level control flow structures. It doesn't have goto, so we can't directly connect those things. Finally, variables. So in LLVM, local variables have function scope. So if you define a variable in one basic block, it's accessible in other basic blocks in that function. And in JavaScript, it turns out local variables also have function scope. So hooray, we found one thing that actually is identical between these two languages. And that's nice on the one hand, but it's actually ironic. So many people complain that JavaScript made the wrong choice for a script language when it decided to do function scope as opposed to block scope, which is what C has, for example. So ironic or not, at least there's one area where there's no challenge in connecting. OK, so how do we actually get around these multiple differences and mismatches? So let's look briefly at a very small sample of code to get an idea of what the translation could look like. So this is a bit of LLVM IR, just silly little function, receives a pointer to a 32-bit integer. It does a load, it does a shift, and then it does a call and returns the output. In JavaScript, it could look like this. So the shift turns into a shift. That's pretty obvious. The function call is a function call. The return is a return. The only thing that might seem odd is this heap thing over here. So what that is we use a singleton array to represent all of memory, basically. So whenever you read from memory, we just read from that array. To write to memory, you just write to it. So that basically represents memory for us. So we translate the load in LLVM IR to a read from a JavaScript array. So there is, in fact, an almost direct mapping between one thing in LLVM IR when it gets lowered to one thing in JavaScript. So often it is actually fairly straightforward. But let's look at a slightly more complex example. So now we're going all the way back to the original source code. So this is a kind of silly little code sample in C++. You have an array of 5,000 floats, and we just loop over it and add 1 to each element. So this isn't anything clever, but just for example purposes. This would be translated to something like the following. So we have a float32 array, a JavaScript typed array that represents, in this case, 5,000 floating point values. So that will represent memory for us. And we translate the function main into this code. So at first glance, this might look kind of different. It doesn't even have the same shape, doesn't look like the same thing. But it's easy to actually to look a bit closer and see that this is a close match. So for example, the loop goes from 0 to 5,000. And over here, the variable b starts at 0, is incremented by 1 in each iteration, and the loop continues up to 5,000. So b is basically the loop variable I. And you can see that we read from this typed array here. We add 1, and we write back. So that is basically the plus equals 1 over here. So even in a slightly more complex example, you can see how things match up. But again, there are some odd things. For example, what's this or 0 operation here that looks kind of weird? So as I said, JavaScript has only doubles. It doesn't have integer types at all. So if I want to get the right behavior of an integer variable, I need to do something. If I just do b equals b plus 1, if b were big enough, that would just turn into a very large double number, larger than a 32-bit integer. But the OR operator actually gives us sort of a little hack or a trick to solve this. So the OR operation coerces its inputs to 32-bit values. That's how it's defined in the language. And then we OR with 0, so we don't change any bits. So basically doing OR 0 is a quick way to make sure something is a 32-bit integer. And therefore, we do it over here, and then b will behave exactly like a 32-bit integer in C. And likewise, over here, we do b or 0 to make sure it's a signed comparison as opposed to an unsigned one. So this is JavaScript, but it's actually kind of a particular style of JavaScript, and it's actually been formalized, and there's a spec for it and a type system. It's called AsyncJS. So again, it's just JavaScript, but it defines formally where all these OR zeros need to show up. So for example, if you write a compiler to JavaScript and you decide to emit AsyncJS, you can run the type checker to see if you missed any of these OR zeros. And if you missed one, that could be bad either for correctness or performance, so this is pretty useful. And likewise, a JavaScript engine could type check the input it sees and optimize that code pretty well. So I've showed you some code samples about JavaScript as a compilation target, but it's important to realize that JavaScript was never intended to be a compilation target. It began as a slow, interpreted language, tiny little scripts and web pages. That's basically how it began in the 90s. But there was a lot of competition in the browser space, which led to JIT compilers, which were much faster, and eventually type specializing JITs. So basically, type specializing JIT looks at the types actually used at runtime. If you have a loop that uses an integer, it'll see that it's just an integer, and it can then emit code that uses integer math. So it can be much faster than an interpreter that runs that code. So these type specializing JITs really made JavaScript engines faster. And that architecture of compiler is very good at statically typed code. In fact, if you ask a JavaScript engine dev, they'll typically tell you if you want your code to run fast, don't mix up types, don't use the same variable for a double and a string and an integer. Keep the code sort of statically typed, but implicitly, because you can't write the types. So these JITs are actually good at statically typed code, even though we're talking about a dynamic language VM. And the nice thing for us is that that is exactly what LLVM bitcode compiled to JavaScript is. It's statically typed. We began with a statically typed language. We preserved that feature as we translated it down to JavaScript. So again, this was never the goal of the industry to have JavaScript as a compilation target, but the industry sort of went in this direction of making JavaScript faster and faster, and that happened to be to generate this tech that is very good for running compiled JavaScript. Let's talk briefly a bit more about speed. So aside from sort of the general terms that I just said, concretely, there's actually several reasons why this type of code can be very efficient. So I mentioned that OR 0 trick before. It's good for correctness, but it's also actually good for performance, because a JavaScript engine can see x plus 1 OR 0 and just immediately emit a 32-bit integer plus, assuming it knows x is an integer. If it knows that, then it's OK to just do an integer plus. It doesn't need to check the type. It doesn't need to do all the other complex operations that typically a JavaScript engine VM would need to do. Also very crucial, a load in LLVM-IR, as I've told you, becomes a read from a typed array in JavaScript. And typed arrays in JavaScript are very easy to optimize because they are actually the one thing in JavaScript that has a type. you define this as a float 32 array, or this is an int array. So JS Engine, when it sees a typed array read or write, it can actually emit something very close to a read in machine code. So it might need to do a bounds check in some cases, so it might not be the same, but often it can even eliminate those. So we get pretty close to turning loads in LLVM IR to actual reads in machine code, which is exactly what we want. Finally, the model that I've told you about, basically using typed arrays to represent memory and so forth, gives us a memory model that's identical to LLVM. So it's this flat C-like model with aliasing. So instead of reading two 32-bit integers, I can read a single 64-bit integer and split it up, et cetera. And because we support everything that C's memory model does, we can just run the entire LLVM optimizer on the code, which can make it a lot faster and also can actually do things that handwritten JavaScript couldn't, because the LLVM optimizer knows types and can do a lot of clever things. So that's another reason why compiled C into JavaScript can be very fast. So here are a few benchmarks showing what the current state of speed is. Zoom in. So these are all written in C++, compiled either natively or to JavaScript. And in JavaScript, they're running on either Firefox or Chrome. And these are how many times slower than native. So 1 is native, and lower numbers are better. And you can see that both Firefox and Chrome on many or most of these benchmarks are within the 1 to 2 times slower than native range, which is quite good, I think, for a dynamic language VM. In fact, on several of the smaller ones, they're really very close to native speed right now. On a few of the larger ones, there's more variability, but even there on most of them, it's about half the speed of native. So it's getting to the right area, and this is much better than it was a year or two ago. There's a lot of momentum here to speed up JavaScript engines, and as I said, this is sort of an area that makes sense for them to optimize because they have these type specializing JITs. So we can expect this performance to get even better over time. Okay, so we've talked about the type of code that's generated. I want to talk about how Emscripten, integrates with LLVM. And to talk about that, let's talk a bit about the code base itself. So the compiler is open source. It's dual licensed to MIT and LLVM purposefully so that we can share code where that makes sense. The project began in about 2010. And actually, what I'm not talking about here is actually most of the code base. So most of the code base is the libraries and the tool chain. So we emulate OpenGL and WebGL and a lot of other things that are not relevant to the core compiler itself. So the compiler and optimizer turn out to be a fairly small part of the code base, but of course, a pretty interesting part, at least from my perspective. So this is what the compilation process looks like. We take LLVM IR, we run that through the Emscripten compiler. It generates JavaScript. As I said before, it sort of lowers it more or less 1-to-1. We then run that through our optimizer, which takes as its input JavaScript and emits JavaScript, but hopefully faster JavaScript. And actually, the compiler and optimizer are written themselves in JavaScript. And probably there's some people here that are thinking, wait, that's not how you typically write an LLVM backend. Why is this written in JavaScript? Why is it taking as input LLVM IR? Why isn't this the proper way to write an LLVM backend? So there are actually 3 compilers from LLVM to JavaScript that I'm aware of, at least 3 that are publicly known. And they each have a different design, which I think is interesting. So I'd like to talk a bit about that, and later on, I'm very curious to hear people's feedback on which of these architectures makes sense for LLVM today. So Mandrill is a closed source compiler. It's basically a typical LLVM backend. It uses table gen, the selection DAG, just like the x86 and ARM backends. It uses all that common shared backend infrastructure. It just happens to emit assembly that looks like JavaScript. That's sort of your typical backend. The Duetto compiler processes LLVM IR. So they wrote a backend in C++, but it works basically like the C++ backend in LLVM now. It just goes over the LLVM module object and lowers one thing in LLVM IR to another thing in JavaScript. So it doesn't use all that shared backend infrastructure. And Emscripten, as I said, basically does the same as Duetto, and then it processes IR, but it does it in assembly format. So we export it out from LLVM into text, and we process the text. So why did we choose that? That might seem kind of strange. So basically, as I said, the project started in around 2010. I wasn't aware of any other compilers doing similar things at all. So basically, I didn't know if this approach to compile to a script language of all things could actually work, and if it could work, what would even be an efficient model. So I wanted the ability to just create a new code base from scratch, to make it as flexible as possible, to just experiment with as many ideas as I could. And this did help prototype and test a lot of things. So we've tried a lot of memory models, for example, of using JavaScript objects to represent objects in C, so each struct can become a JavaScript object. We've tried many different approaches, and just having this little script code base was kind of good for that. But this has downsides too. So we basically need to do ourselves what the shared backend infrastructure can do. So for example, when we run into something that we can't directly translate to JavaScript, we need to legalize it in our code. We can't use the legalizer that LLVM's backends do. So it feels like we're doing something wrong when we're doing that, but in the architecture that we have, that's sort of what we end up doing. So perhaps we should be doing things slightly differently. And to sort of talk about that, I want to talk about 3 optimizations that Emscripten does that we found are very important for JavaScript. So basically, the motivation for talking about them is that whatever the best architecture is for compiling to JavaScript from LLVM, we want to be able to implement those in a good way, because those really matter for performance in modern JavaScript VMs. In fact, each of these 3 that I'll be talking about can make even a 10 times difference in performance. It depends on the code base, but can be very substantial. So the first of these 3 is the reloop optimization. So to understand what that does, it basically recreates loops, but to sort of get a concrete picture of what it does, let's first see what happens when we do not have access to the relooper. So if we have this LLVM IR code here, so we have 2 basic blocks. The first one has some code, and then it does a branch based on a condition, either to itself or to block 1, and block 1 then runs some code and goes right back to block 0, so it's an infinite loop, not something too interesting, but just for example. So as I said, JavaScript does not have goto, so we need to emulate goto somehow. And one way to do that is basically to define a variable, call it label, that basically says which basic block do I want to get to. So we want to get to block 0 to begin with, and then we have an infinite loop that just picks the label and just goes there. So for basic block 0, we execute code 0, then we set label depending on the condition, and we break to get back here, and then we'll either end up in block 0 or block 1. So this does the right thing, but it's kind of clunky. The relooper will emit the following code. So it's pretty easy to see that this is the correct thing. So we'll execute code 0 while the condition is true, which is exactly what the basic blocks tell us. We'll then execute code 1 and go right back to the beginning. So the relooper is very crucial because it allows the JavaScript VM to understand what the structure of code is. It knows what code comes first, what comes later. So without that, if we have, imagine that we have 1,000 basic blocks. So imagine that this list were much longer. It just doesn't know which basic blocks come first, which come later, which are inside a loop, how nested that loop is. So it's hard for it to know how to do register, allocation, and all these other optimizations that a JS engine can do on loops, like range analysis for loop variables. So by recreating loops, we make it possible for the JS VM to actually optimize the way that it wants to. And actually, we've written the relooper code in a generic way because this, of the 3 optimizations I'll be talking about, this is the more general purpose one. And actually, the code is already used by Duetto, for example, which, as I said, is another compiler to JS. So of the 3, this one definitely seems like it doesn't really change your choice of architecture. It could work in an LLVM backend or outside, that's fine. So really the more interesting questions are the other two optimizations that I'll talk about right now. So the second is the expressionize pass. Sorry about the name, I'm not great at naming stuff. So imagine we have this code here. So the variable a receives g of x, and a is used right here, but a is only used once, so it's not used anywhere later. So we can just basically move this g of x into here and get rid of the variable a. It's kind of an unneeded temporary variable. And the same is true for, in fact, all these variables. And what the expressionize pass does is it sort of unfolds that stuff into this complex expression as you see here. Now, of course, this is not always possible to do because you need to make sure there are no side effects, and you need to make sure to respect the order of operations because you're moving code around. So that's tricky. But when it's possible, it can be good. And why is it a useful thing? It both makes the JS engine faster to JIT the code and also faster to execute the code for the simple reason that it has fewer variables to deal with. So when a JS engine JIT sees a variable, it typically needs to process and calculate a lot of info about it. For example, in the lower tier JITs, it might just allocate stack space for every variable. So imagine you have a large function with 10,000 variables. That's just not going to work at all. And even in the higher end JITs, the amount of time it takes them to compile the code depends on the number of variables because they'll analyze all the things that they need to do register allocation. So just reducing variables is very good for performance, and it also lowers code size, which is nice because on the web we're typically sending the data over the network. Finally, the registerize pass does something similar in that it also eliminates unneeded variables, but it does it in a slightly different way. So if we have 3 variables here that are integers, you can tell by the or 0, and one that's a double, you can tell by the plus, because the plus operator converts anything to a number, and as I said, numbers are doubles in JavaScript. Basically, the registerize pass will see that B and C we can just reuse the variable A. We don't need to actually keep A alive after we use it here, and likewise for B, so we can just consolidate this into 2 variables. And this looks like register allocation, kind of, doesn't it? I mean, even the name is kind of the same. But actually, there's a significantly different goal. So it's similar, but not identical. We want to minimize the number of variables. We don't have a fixed set of registers that we need to fit everything into and then figure out when is best to spill. We have potentially an infinite set of these variables, but we just want to use the minimum that we possibly can. So this is not what register allocators typically do. It's a slightly different problem. And why are we facing a slightly different problem? The JavaScript VM will actually do register allocation. It knows what machine it's running on. It knows how many registers there are. When we emit JavaScript, we're emitting something higher level and portable that's not specific. So of course, just like before, eliminating variables is good for speed and size. So 2 last slides. To summarize the issue of optimizations, those last 2 passes require very precise modeling of the semantics of JavaScript, things like the order of operations, which is actually a bit surprising. So for example, the order is different than C. So we have cases in our optimizer where we need to make sure not to do what seems like the natural thing, but in JavaScript, we'd get the wrong code being run. So what I'm curious about, and I'd be very interested to hear feedback from people here, is there sort of a good, nice, elegant way to do something that's very specific to a language like JavaScript in an LLVM backend? Or if the more natural way is just to do it on a JavaScript AST, then that's what we're doing now. So I'm kind of posing it as a question, and again, I'd be happy to get feedback on what sort of the best way to do that is. And I guess to be a bit more specific about the questions, I'd be curious to hear, after I've told you about how our compiler works and optimizes, whether people's overall thought is that the architecture we have now is the better one, or whether we should rewrite and use sort of a typical LLVM backend. And on a related note, would it make sense for us to then upstream some of our code, like the reloop code, which, as I said, is already being used by at least one other LLVM-based project? So please let me know if you have thoughts on any of that. Okay, so just want to summarize. So basically, I've been telling you that we can compile LLVM bitcode into JavaScript. The point of this is that it'll then run in all browsers, and browsers run everywhere. It can even run at high speed, so even though it's a script language, it can be very performant. And this just gets us a way to compile practically anything to LLVM bitcode and then run it practically anywhere, which I think is kind of nice. And if you're interested about this topic, feel free to visit our site. And of course, it's an open source project, so feedback, etc., is always welcome. That's it. Thank you.
We have time for questions, if anyone has them.
Is there any way to interop with some specific APIs used in the initial code? So to map APIs from initial code to JavaScript code. So for example, you've said you use mapping from OpenGL to WebGL. Is there any generic way to do this for other APIs?
Yeah, so basically how we do it is we have a very easy way to interface between a C API that you call from your C code, and you can just implement that in JavaScript. So an OpenGL call is a C call, we just implement that in JavaScript that happens to call into the WebGL code base. So that's sort of the simple way to interface between your compiled code and other JavaScript. But I'm not sure, does that answer your question? Or? Okay, but maybe ask me later, because I feel like I missed something in your question. Okay. Any other questions?
Yeah. So you didn't answer my biggest question, which is when I think of data types in C, I think of structs that, have a virtual method table, floats and ints packed together, unions, that sort of thing. How do you map that onto the JavaScript memory model?
Yeah. So briefly, I really didn't have enough time to get into all these details, I'm afraid. We have the same memory model as C. So if you have a struct that has floats and integers all together, it will literally be laid out in memory in JavaScript identically to how C would do it. Exactly the same. So it'll take the same amount of memory as the C program would. And then because we have basically a JavaScript array buffer, which is just a block of bits, and then we can read from it at this point a 32-bit float, or at that point a 32-bit int. So literally structure exactly the same layout as C. Regarding the other part of the question, things like virtual methods, that's slightly trickier. So we have vtables, of course, but the tricky thing is that, so if a vtable could, in a native build, would have like a function pointer to where we actually execute code, we can't store a function pointer in JavaScript because it's a safe language. So we have another level of mapping where we represent a function pointer by an integer that then has this sort of function table, we call it. So we just look up in the function table and then call that. But yes, we can implement even vtables and C++ polymorphism, etc. That all works, basically.
Yeah, so you had two questions, like basically how to implement this stuff in the backend, or if we believe it's a better idea. So I don't have an answer to that. But I think there are two projects, like there's the NVIDIA PTX backend, which basically has a very similar problem to you, like register allocation, not in terms of a finite amount of registers, basically an infinite amount. Mm-hmm. So that's maybe one place to look at. And I think the AMD R6 300 backend basically has a backend for relooping, or uses relooping in LLVM. So there is some infrastructure used in an LLVM backend. I really don't have any experience of that, so I can't help you with that. But they may be interesting to look into. And then I have also...
Okay, thanks.
Yeah, I also have a question. So I'm interested, like you said, you map everything to double, and that works. What are you doing with this arbitrary integers in LLVM, arbitrary size integers like int 64, for example?
So in 64, we actually... So a 32-bit integer is fine because it fits inside a double. Yes, but a 64-bit integer is something that we need to legalize. So we are presented as two 32-bit integer chunks, actually. So types like that we need to legalize in some manner. So does that answer the question? Or were you asking something more general?
Yeah, I was wondering how general is your legalization? Actually, does it just happen to work for like the integers used in C programs, or is it like, do you support int 173?
So it supports anything that anyone ever filed a bug against, basically, that basically means that it does support things like a 512-bit integer, because that's what the LLVM optimizer generates for SQLite. In our experience, we support things like 33-bit integers, because Mo sent me a test case that does that. So we actually do support a wide set of illegal things, but I would certainly not claim that it's sort of going to handle all the cases, because we've focused on the things that we've actually seen. So it's not perfect. Cool. Any other questions? Or?
So you mentioned 3 important performance optimizations, and I wonder if you have like immediate numbers showing how effective each optimization is, like which one is more important than the other, and how much relative performance benefit each of them brings.
Yeah, so it depends quite a lot on the specific code base, but I can easily show you simple test cases where each of those makes even a 10 times difference. So for example, just imagine you have a very small inner loop that all it does is add some integers. If you don't have the reloop optimization on that, and you have this switch and this variable, it could easily be 10 or even 20 times slower. Likewise with the other 2 are basically focused on reducing variables. So again, the difference could be 10 times slower or more if you have a huge function. If you want more details, I could actually run the test suite with different opts, but that's sort of the big picture.
Right. So yeah, I understand that for micro benchmarks, there will be huge differences. But like for example, the Unreal demo you have shown, like if we take the FPS as the only metric, which is probably unfair, but then can you roughly tell us if we turn off relooper, like how much FPS will it drops to, things like that? Yeah,
so we actually, I think, ran that without relooping at some point. If memory serves, it was maybe 3 to 4 times slower, something like that. But a lot of that is because that demo uses graphics, and so about half the time is spent anyhow on the GPU. So the CPU code is probably, I don't know, 6 times slower or so, but because half the work is on the GPU, you don't notice it quite as much. Yeah. Does that answer the question?
Yeah, so that says about the relooper part. What about the rest too?
Frankly, that code base would not even be able to load without the other 2 passes, because there are some very huge functions in those that have tens or dozens of thousands of variables. The JS engine will actually just run out of memory, both Firefox and Chrome, if you don't really aggressively eliminate all unnecessary variables. So in this case, it's not even speed. It literally just crashes. Yeah. Cool.
Hi, I have 2 questions. One question is, how are flaws in the source language translated to JavaScript? If there's any flaw in the source, so say there's a security loophole or something like that, how is that preserved, or how is that managed when you translate that bitcode to JavaScript? And the second question is, do you do any hints for garbage collection within the translated code?
So I'm not fully sure I understood the first question. Did you mean any security, like
so for
Stack
example,
Overflow or something? Or?
A Stack Overflow or remote code execution or...
Yeah, so we're the same as C. So potentially you could cause a buffer overflow and do any other sorts of things. However, there are some things that we are safer. So for example, as you actually can see in the code, somewhere here, yes, as you can see in the code here, we use JavaScript vars. So those vars are stored in the JavaScript stack. So there's actually no way to sort of overwrite those. For example, they're stored separately. So in a sense, we get some additional amount of safety from that. However, if you have something on the stack that you take the address of, that means we can't create a var because we can't take the address of something in the JavaScript stack, and then it'll be in the C heap, which means you could overwrite it. So I would say overall the security aspect is very, very close to what C has, but maybe there's a few cases where it would be better. We also use JavaScript function calls for for function calls, so you can't just do too many function calls and blow the stack in that way. So whenever we use a JavaScript stack, we're slightly safer. But I mean, I'm not a security expert, so I'm not sure how beneficial that is. And what was the second question? Sorry.
JavaScript has a notion of garbage collection, right? So,
Oh, yeah.
how do you handle that?
Yeah, so we basically don't use it. So when we emit this type of code, as you can see here, we don't actually allocate any JavaScript objects. We allocate a singleton float array, but aside from that, we don't constantly allocate them. So one of the reasons this code is faster is it doesn't use the garbage collector, actually.
Okay, this is the last question.
Okay. How do you handle C++ exception handling?
Yeah. So we basically support it using exceptions in JavaScript. So we obviously need to do quite a bit more, but overall, whenever you do an invoke an LVM IR, it turns into a try-catch in JavaScript with a function call, so we can roll back the stack, unroll the stack. And then we, of course, need to add code to check for the type of the exception and so forth. So we use sort of standard exception handling, but we do use JavaScript native exceptions just to make it simpler and hopefully faster, although I haven't benchmarked that. But it basically works in that approach. Cool.
Great. Thank you.